Chapter 6, Part 2. Continuing our look at orbits and circular motion, let's start with circular motion around a roller coaster. So in this case, these fun little friends are cruising their way around this circle track on the roller coaster, getting very dizzy, I am sure, and we're going to try and figure out their apparent weight. Because it turns out your weight kind of changes, right? When you're at the top, you feel a little bit lighter. When you're at the bottom, you feel a little bit heavier. So let's take a look at that. So if we do some free body force diagrams, at the very top, the weight is going down because gravity is pulling them down. But the normal force, the car pushing on them, is also pushing them down. So we end up adding the normal plus the weight, and that pushes their force net down. Okay? So their apparent weight would be equal to the normal force, and the normal force would be equal to the centripetal force, right, F sub c, minus their weight. So that would be mv squared over r minus the weight is their weight apparent. At the bottom, the apparent weight would be equal to the normal force, but now the normal force is going up, right? Because the net force is going up, the weight goes down, but the car is clearly pushing them up, so we need a big normal force to make up this force net arrow going up. So that'd be the weight plus the mass times the acceleration centripetal. So that's the weight apparent is equal to the weight plus the mass velocity squared over r. Or I could say the mass, I could pull the mass out because weight is equal to mass times acceleration due to gravity. So that would be weight apparent is equal to mass times acceleration due to gravity plus v squared over r. Basically, this is just the acceleration plus the acceleration. And at the bottom, I know I'm going to end up with a bigger value, so I'm adding them together so that I feel more apparent weight. At the top, I'm subtracting the weight out, so I end up with a smaller value, right? The centripetal force is still pushing, but then the weight is going the down, which is the negative direction. Okay. So this has to be the positive one. That's what actually holds them in the car. If that was negative as well, then it'd be negative plus negative is negative, and then they'd be falling down onto the ground, which would be bad for the liability of that amusement park company and their safety and ethically. So we call that a critical speed. So the critical speed, v sub c, is how fast does that car have to go for them not to fall out? We don't want them to fall out. So how would we find v sub c? Well, I know that the apparent weight at the top of the car, because that's the one that I'm worried about, that's where they would fall out, is mv squared over r minus the weight. Then I can say they will stay in as long as their apparent weight doesn't get below zero, right? I have to stay with a positive apparent weight. They have to feel like there's something there, and then they'll start coming back down. So I got to set it as, bigger than zero. And then I can say that the weight here can turn into the mass times the acceleration due to gravity. And then I'm going to solve for v. And I'll figure out what my apparent weight, my critical speed or velocity of critical speed would be. So to solve for v, I am going to add mg to both sides. So that ends up over here with mg equals mv squared over r. Now I've got mass on both sides, so those masses will cancel. It turns out the critical speed doesn't matter how large the person is in the car or how massive they are. Now I'm going to multiply both sides by r to get that gone. And I'm left with rg equals v squared. And I need to take a square root there, which leaves me with a final answer of v critical equals the square root of gr, or rg. You could phrase it any way you want. Okay, so that is going to be a helpful equation. The critical speed for not falling out, because that'll also be equivalent to some orbiting speeds to keep the object in orbit. So I'm going to go ahead and actually add that one onto my physics everything sheet, and I'm going to add it in with the centripetal acceleration one, just so I remember that these are all kind of related equations. I'll note that as V sub c equals the square root of GR. I'm just adding it in the margins there, so I've got it. Since it's not on here, it's unlikely that the AP test would ask me about it, but it's helpful to have. Okay, let's do a stop and think. A car is rolling over the top of a hill at a constant speed v. At this instant, is the normal force bigger than the weight? Is the normal force less than the weight? Is the normal force equal to the weight, or we just don't know? Okay, so I could think about this a few ways. The first way I could think about it is, how does it feel to me when I'm going over the hill and I get that little like whee, like going up and then coming back down? So I have a feeling that the normal force is going to be less because it feels like I'm lighter. And so my gut feeling, based on my experience, is the normal is less than the weight, right? My weight remains the same, 145 pounds, but I feel lighter when I'm going up and then coming back down. But I'd like to kind of prove it to myself in another way. So in this case, I am going up on the outside here. So in the amusement park, when the person was here, they were going on the inside, and the centripetal acceleration was to the center, right? So now they're on the outside, and so they're going to have the weight going down, but their velocity wants to keep them going straight, right? So they're going to want to keep going straight here. And over here, they wanted to keep going straight here. And the car would have moved from here down to here. So they would feel like they're being lifted out. So that feels accurate. The normal force should be less than the weight force. Cool. So that kind of tracks based on my understanding of centrifugal acceleration, which is fictitious, but feels real. All righty. I guess the other way of thinking about it would be, yeah, here they're on the inside of a turn. So if I did it the other way on the outside of the turn, it would go the other direction. The centripetal acceleration would be here, but I'd be here, which means I would have less net force going up. Okay. All right. Projectiles being launched at increasing speeds. Okay, good. So now we're going to get into things going into orbit. So if I throw an object off of a tall building here, and I do projectile motion, it follows like a parabolic path to hit the ground. Now, if I could throw it harder, it would go further sideways before hitting the ground. Well, eventually, I could throw it hard enough that the falling rate is equal to the curve of the planet rate, right? And then it would go all the way around before coming back. So it would be, the object would still be falling all the time, but it would never get any closer. I would go out here and I would fall that much. And then I would, sorry, let's do a different color. I would fall the blue amount, right? That would be my acceleration due to gravity, or my distance fell. And then I would go out here. No, I'm down, never mind. I'd go over here, I'd go out that much. And during that time, I would fall that much. And I would just keep staying an equal distance away from the planet. And when that happens, we say that that object is in orbit. Now that only works if you're not encountering air resistance, right? You have to get outside of air resistance, outside of our atmosphere, because otherwise you would get slowed down by air resistance, and then that would slow your path down and you'd spiral onto the planet. So that's what happens when like meteorites come in. They kind of pull in at a sideways and they spiral down towards the planet, and mostly they burn up, but occasionally a small amount would come down and hit the ground. So we know that the force of gravity is always towards the center of the Earth, and that's why we kept getting those arrows going like that, right? Always towards the center. So zooming out, weight is always towards the center, so the force of gravity is always towards the center. All right. So let's talk about acceleration. Acceleration, in this case, is gravitational acceleration, or g, and that's equivalent to the velocity of the orbit squared over the radius, which should look familiar because that's the same as centripetal acceleration, right? The centripetal acceleration is towards the center of the circle. In this case, I have a circle. I have the force towards the center of that circle. Same equation. It's just that the velocity is of the orbit. Okay? And then I could solve for that and say velocity of the orbit is equal to the square root of g times r, the same way that I solved for it previously, where g was acceleration due to gravity. So I'd multiply r over, take the square root, and I'm ended up with that fun equation. Hooray. Now, I could also say that the period is equal to 2 pi r, that's the distance, over velocity of the orbit. That's a manipulation of velocity equals distance over time. And then distance is 2 pi r over period, and then multiply the period over here, multiply the period over to here, divide both sides by velocity over to here, and I'm left with that equation. Okay, then I can plug in for the velocity of the orbit my square root gr, since I found that over here, and I could solve out that 2 pi square root of r over g is equal to my original period. So that's another option of a fun equation that might come into use. 2 pi root r over g for the period. Speaking of putting things into use, a satellite is in low Earth orbit. Which of the following changes would increase the orbital period? Oh, good. We have an equation for orbital period. It's right there. So things that would increase the orbital period, that would be the radius, right? If I increase the radius, okay? Let's see. Increasing the mass of the satellite, no. Increasing the height of the satellite about the surface. Height from the surface feels like radius of a circle. That one's looking good. Increasing the value of g, that would be the acceleration. And if I accelerate it more, it'll go faster, and that would increase, or no, that would decrease the period. That would need less time, so that would be bad. No. So I'm left with B. Increasing the height of the satellite around the Earth surface, that means it has to go a further distance, and that would logically take a longer time. Good. All right. Now we can introduce a new concept, which is Newton's law of universal gravitation. So the law of universal gravitation states that the force due to gravity is equal to a universal gravitational constant times the mass of the first object times the mass of the second object divided by the radius or the distance between them squared. So mass of object 1, mass of object 2, and then there's the distance between them here to here, right? The bigger the objects get, the more massive they get. That's actually not more massive. That's just me moving my fingers in and out. But let's assume bigger means more massive. I'd actually have to hold things and give myself more mass. So now I've got a calculator. This hand's more massive. So more massive means now there's going to be more gravitational force. Less massive means now there's going to be less gravitational force. If things get further apart, there's going to be less gravitational force between them because the radius or the distance has increased, and that's on the denominator. If they get closer together, then there's going to be a lot of gravitational force between them. So what kind of things have the most gravitational force? Things that are really close. If I can get that radius really, really low, So like, why do you feel so much force from the Earth, even though the sun is much larger than the Earth? Well, because you're right on top of the Earth. The distance from you to the Earth's surface is very small. So that's a small number on the denominator, and that makes a bigger force of gravity. If you are really, really far from the sun, like you are when you're on the Earth, that's a big number. Something over a big number in the denominator makes a small force of gravity. All right. We call that the inverse square law. So that relationship where the force of gravity is proportional to 1 over the radius squared is the inverse square law. You could also express it as y equals a over x squared. So if this is my x value here, and this is my y value, if my x value starts at 1, then my y value gives me an answer of a. If I double my x value, then 1 over 2 squared is 1/4 of a. Okay, so 2 gives me 1/4. If I cut my x value in half, a over 1/2 squared, a over a quarter is equal to 4 times more. So that's 4a. All right, so I end up with this little inverse square graph here that's not very nicely drawn, but pretend that it's nice and smooth and tracks more clearly. And there you go. All right, let's do some samples. Gravitational force between two people. Oh, the other big piece is that we have a value for the gravitational constant. The gravitational constant is 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. That's a tiny itty bitty number, which means gravity only works when things are really big, like planets or stars. Are you gravitationally connected to your pencil? Yes, you are. You are attracted to your pencil, and it's attracted to you. Equal and opposite forces. However, it's a very small force because the pencil is so not massive and you are so not massive. You are so small in the scale of the universe. I'm sorry. All right. So let's find the gravitational force between two people, see how well attracted you are to the person sitting next to you. You are seated in your physics class next to another student 0.6 meters away. Estimate just how attracted you are to that person gravitationally. That's the kind of attraction that we can measure in physics. So the magnitude of gravitational force, assume you each have a mass of 65 kilograms. How cute, you're the same size. So I know that the force of gravity is equal to big G m1 m2 over r squared, which is equal to 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared times each mass, 65 kilograms times 65 kilograms, all of it over r squared, the distance of 0.6 meters squared. Okay, so basically this is a pretty easy problem. The only tricky thing is that we've got these darn exponents out here. That's scientific notation, 10 to the negative 11th. That's going to make things tricky. So I'm going to multiply the top parts together, the whole number parts, and then I'm going to keep that times 10 to the negative 11th, and then I'll deal with it later. I'm going to deal with the bottom, and then we'll go from there. So on the top, I got 6.67 times 65 times 65 gives me 28,180.75 times 10 to the negative 11th. Kilograms squared, kilograms will cancel. Meters squared will cancel, although this is still squared. The 0.6 is still squared. So that leaves me with newtons over 0.36. I got rid of my meters squared, so that's good. Okay, so now if I want to move this decimal place 1, 2, 3, 4 over 2.8, that would be 4 positives there. So a negative 11 plus 4 changes that into a -7, sorry, -7. And then we'll divide that by 0.36, giving me 7.8 times 10 to the -7th newtons. So that is like 1/1,000,000th of a newton, not even 1/1,000,000th. It's 8/10,000,000ths of a newton. It's very small, less than 1/1,000,000th of a newton. So very small attraction force. Sorry, maybe it's not meant to be. Or maybe there's some other factor that might play in that's not gravity. Use your charm. Okay. So gravitational force of the Earth on a person. So, okay, now we're dealing with the Earth. The Earth is much bigger. This is good. I feel better about the Earth. It's large. Look at that, 10 to the 24th kilograms. I think this might play in a little bit better. Same equation, F sub g equals big G m1 m2 over r squared. 6.67 times 10 to the -11th newtons meters squared over kilograms squared times the mass of the first object is the person. The person is 60 kilograms. The mass of the second object is the Earth, which has really been getting heavy recently. 5.98 times 10 to the 24th kilograms. That was a joke. The Earth can't get any heavier unless it pulls in some extra asteroids or something, because all of the mass on the Earth stays on the Earth, except for astronauts, maybe. Space trash. Divided by the r squared, which is the radius of the Earth, 6.37 times 10 to the 6th meters squared. That squared is important to remember. All right, I know that units will cancel out, meters will go away, kilograms will go away, leaving me with newtons. I am once again going to deal with whole numbers at a time, and I'm going to remember to square both parts. So the squared goes to the 10 to the 6th, and the squared goes to the 6.37. So that'll leave me with, on top, -11/24 will be 10 to the +13 newtons times 6.67 times 60 times 5.98, 2,393. 93, please. Then on the bottom, 6.37 squared is 40.6 times 10 to the 12th, because 6 and times 2. Okay, so this one's actually going to work out nicely. 10 to the 13th and 10 to the 12th, I can just cancel that one and make that 10 to the 1, right? 12 and 13. Subtract out, gives me 10 to the 1. So 2,393 divided by 40.6. 2,393 divided by the answer, 58.979, but then I got to multiply it by 10 because I got 10 sitting there. Gives me 590 newtons. All right. Now, does that seem like a reasonable weight, a reasonable force of gravity of a 60 kilogram person? Well, since I know that the acceleration due to gravity on the Earth is 9.8 meters per second squared, 9.8 times 60 would give me right around 590 newtons. Seems like I'm in the right zone. I could double check it and just see. 590 divided by 9.8 is 60. Choo! Feeling pretty good about that one. So that looks pretty reasonable. All right. Another piece to mention, I can take that force of gravity and I could say that, well, the force of gravity is also equal to mass times acceleration. And since mass times acceleration leaves me with the mass of the person over here and the mass of the person over here, then I could say cancel that, cancel that. The acceleration of gravity is equal to the gravitational constant times the mass of the planet or the object that you're on over r squared. So let's check that. Acceleration due to gravity of a planet is equal to the gravitational constant times the mass over the radius of the planet squared. Stop and think. Rank in order from largest to smallest the free fall accelerations on the surfaces of the following planets. Okay, free fall accelerations, that means acceleration due to gravity. We're looking at our thing, factors that will matter. The gravitational constant, but that's a constant, the mass of the planet, and the radius of the planet. And which one matters more? The radius matters more because it's squared. So I'm just going to write down here, acceleration is proportional to the mass over the radius squared. Okay. So this one, 2 mass over 2r squared would be 2 mass over 2r squared, which is the same as 4r squared. Okay. So that's 2 over 4, which gives me 1/2 for my number values. M over 2r is going to be mass over 2r squared. 2 squared is 4, so that's 1/4. 2m over r would give me 2m over r squared, or a total value of 2. And then this one, m over r squared, gives me a value of 1 mr. Okay, from largest to smallest. Great, so the largest is going to be B in order. B is the biggest, is bigger than the next one, which is A, which is bigger than the next one, which is D, which is bigger than the next one, which is C. So if I want more gravity, I want more massive planets, and I want them to be smaller. And if I have to decide, smaller is more important than mass, because that part gets squared. Nice. Feeling pretty good on that. I think, yeah, we're ready for our last little piece, which is gravity and orbits. Let's stay in space and power through this last little component. So, gravity and orbits. I know that I have the force of gravity, which we've already talked about. And then I've got the force due to centripetal acceleration, which is force equals mass times acceleration centripetal, which equals to mass v squared over r. And that's just showing that the orbital motion is due to the force of gravity. Okay? So let's kind of prove that. So if I set them equal to each other, since that's a force and that's a force, and those two forces are both working to pull things towards the center, that g m1 m2 over r squared is equal to m v squared over r. I want to solve for v. I want to solve for the speed of the satellite. So I can start by going through and saying, well, there's a mass and there's a mass, so I can take those masses away. On the bottom, I've got an r and I've got r squared, so I can take one of those r's away. Now I'm left with v squared equals g m2 over r. So I need to take a square root there and a square root there, and I'm left with v equals the square root of big G times the mass of the planet over the radius of the planet. So this would be like mass planet, radius planet. Nice. Because I've already taken out the mass of the object, the mass of the satellite itself. Cool. That looks pretty good. And I guess that should not be the radius of the planet. It should probably be the radius of the orbit, right, to the center of the planet. So I'm actually going to adjust that. Oops. Erase, please. No! Tell me I didn't lose it. Ruh-roh. You guys remember that part? I'm going to say that you remember that part. I showed you the math. The big piece was V equals square root, big G, the mass over the radius. Okay? And the radius is of the orbit. Cool. We're going to pretend that that was all good. Technical piece. Lovely. And that's the velocity of the orbit, right? Or the velocity of a satellite. All right. So I can also then say that I know that velocity is the distance over time. So I could set the velocity equal to the velocity centripetal. So here's my centripetal velocity. Here is my, sorry, just to clarify, here is my equation for centripetal velocity, 2 pi r over t. And I stole that one from over here. Velocity is 2 pi r over t. That's the velocity using the circumference of the circle and the period. And I set it equal to the velocity of the orbit, since distance over time gives me distance 2 pi r time period. Great. All right, so then in green, in order to set those two velocities equal to each other, I'm going to square that to get rid of the square root. So that'll take care of my square root part. I'm left with that squared. GM over r equals 2 pi r squared over t. You can do a little bit of tricky math. Multiply this r over to here. That gives me r cubed. Divide by g down to here. Divide by m down to here. Multiply my t squared over to here. And I'm left with a nice friendly equation. T squared equals 4 pi squared over gm times r cubed. Oh my God, that looks like the worst equation in the world. It doesn't look like the worst equation in the world. There's just a lot of squareds and pi's and variables. So that equation would relate period to orbit radius, right? Another way of phrasing that is that the period squared is proportional, directly proportional to the orbit radius cubed. Okay, so let's do a little example. I think we just have 2 more examples and we're there. So locating a geostationary satellite. Communication satellites appear to hover over one point on the Earth's equator. A satellite that appears to remain stationary as the Earth rotates is said to be in geostationary orbit. What is the radius of the orbit of such a satellite? Okay, so I need the radius. And I am given no numbers, but I think I can figure some out. So I'm not given anything, but it stays directly over one place on the Earth. Well, how long does one place on the Earth take to go around? I'm given a period, which is one spin of the Earth, and that is 24 hours. I'm also given the mass of the Earth. I'm not given it, but I can remember it from a previous problem by looking back and looking it up. The mass of the Earth was 5.98 times 10 to the 24 kilograms. 5.98 times 10 to the 24 kilograms. And then I can remember that big G was 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. I'm going to use that gnarly equation from up above, right? Because I need radius, I've got period, I've got G, I've got M, I know 4 pi. Okay, so this one's going to be quite a math thing, but T squared equals, zoom out a little bit, 4 pi squared over GM times R cubed. Now, T is 24 hours. I'm looking here at my time and thinking, I want the radius, right? The radius should be in meters. Where do I get rid of hours? Do I need to convert that to seconds? Because newtons, oh, here it is. Okay, so it breaks down to newtons this gets down to definition of a newton. Newton is kilograms meters per second squared, right? So I'm going to make that kilograms meters per second squared, which means this unit becomes kilograms on top, 2 kilograms on bottom. So I'm going to get rid of one of those. Meters on top, meters cubed over kilograms seconds squared. All right, now that works. I am going to grab a power cord from my computer so we don't lose power. Apologies, apologies. We're so close. Okay. So now I can make it work, but I do have to convert my 24 hours into seconds. So there are 24 hours in a day, but I'm going from hours to seconds. So I need hours. 1 hour is 3,600 seconds. That's 60 seconds in a minute, 60 minutes in an hour. 2,400 times 3,600, 24 times 3,600 will give me my answer in seconds. 24 times 3,600, 8,6,400. All right, so I over here have 8,6,400 seconds squared equals 4 pi squared over G, 6.67 times 10 to the negative 11 meters cubed over kilograms seconds squared times M, the mass of the Earth, 5.98 times 10 to the 24th kilograms times R cubed, which is what I'm solving for. Okay. So now basically we just get into a bunch of gnarly math. If you guys are cool with just trusting my bunch of gnarly math, plug in a bunch of stuff into the calculator, square this, multiply these together. I should do it. Dang it. I shouldn't. And then you end up taking the cube root of it, and we end up with an answer that R is equal to 4.22 times 10 to the 7th meters. that would be equivalent to 42 million meters up in the sky, or since there's 1,000 meters in a kilometer, 4,200 kilometers up, minus the radius of the Earth. So take that away. All right, I think that puts us in pretty nice shape. Let's take a look at our last stop and think. Each year, the moon gets a little bit farther away from the Earth, increasing the radius of its orbit. How does this change affect the length of a month? So I don't love this question because this is assuming that a month is like precisely linked to the circle of the Earth, or sorry, so the rotation of the moon, the circle of the moon, and it's not. We have 12 months, but closer to 13 moon rotations. The moon rotates every like 27 and a half days, 28 days. So it doesn't affect the month. The length of a month stays the same. So part of me wants to say like, well, the length of the month stays the same because people made that up. Why is February 28 or 29 and why is other months 30 or 31? I don't know. So part of me wants to say the length of the month stays the same. They're not connected. If they're talking about like the orbit of the moon, what does it do to the time period of the orbit to go around? A greater radius will mean that it takes more time to go all the way around. And then we would say it gets longer. So not the month, but the period, the period of the moon. So the period of the moon gets longer, but I'm going to say that the month stays the same. Weird question. Okay. A hunter and his sling. Oh boy. Hold on to your pants. This one is gnarly. A Stone Age hunter stands on a cliff overlooking a flat plain. He places a 1 kilogram rock in a sling, ties the sling to a 1 meter long vine, then swings the rock in a horizontal circle around his head. The plane of the motion is 25 meters above the plane below. The tension in the vine increases as the rock goes faster and faster. Suddenly, just as the tension reaches 200 newtons, the vine snaps. If the rock is moving towards the cliff at this instant, how far out on the plane from the base of the cliff will it land? Okay, so I'm going to separate this into a couple pieces. First, I'm going to figure out what's going on with this swing around, and I'm going to use that to figure out the velocity of the rock coming out, because I need the velocity coming out so that, okay, so basically what's going on is I'm going to draw this first. Here's my Stone Age hunter. I think in less PC terms, we would call him a caveman. He's swinging this thing around, and then the rock goes out and falls down. I know that this height is 25 meters, and I'm asked how far this is. So that is the x coordinate. However, in order to do that, I can figure out the time, right? Because I know that it's going to fall horizontally due to the acceleration due to gravity. And then I can figure out the time of the fall, right? So I'll need the time of the fall first. Then this way, I can remember this from kinematics. I need the velocity in the x direction so that I can say that the velocity is equal to the distance over time, and I'll have the time from over here, and I'll have the velocity because I calculated it, and then distance is equal to the velocity, times the time. Okay, so that's how I'll get the distance. Sorry, the distance is the x value. So that's how I'll get that distance. But I need to figure out the exit velocity. So now I got to do the exit velocity. The exit velocity is based on the tension in the rope and swinging in this big circle. So I'm going to start with a diagram. So I know that I have a force down, which is the weight of my rock. And then I have a tension on the rope. And the tension I would think would go like horizontally, but if it's pure horizontally, then the rope's going to go down. So it has to go at an angle up here, right? So I have to have a tension force there. And I know that that value is 200 newtons. The weight is based off of a 1 kilogram rock. So the weight is equal to mass times the acceleration due to gravity, which is equal to 1 kilogram times 9.8 meters per second squared, which is equal to 9.8 newtons. Okay, so for this tension on the rope, since it's not perfectly, and it's going to be much, much longer, right? I'll make that bigger since this is 10 and that's 200. I could draw my X and my Y components of it, because what I really care about is this horizontal component of it, because that is going to determine how big my circle is. Because the string, like if I take something on a string and I spin it around, gravity is going to pull the end down a little bit. It's not going to be totally horizontal the entire time. So I got to have that, take that into account. So I know that the vertical component is 9.8 newtons down. So that has to be balanced by 9.8 newtons up, right? Then that gives me an angle theta there. But I could also just figure out this value, this horizontal component of the tension by doing a squared, b squared, c squared. So I'm going to try that. I'm going to say 9.8 squared plus the horizontal tension sub x squared equals 200 squared. So 200 squared minus 9.8 squared, and then take the square root of that, gives me 199.96. So it's almost the same. 199.96, nope, 0.76, excuse me, 76 newtons horizontally. All right, so now I've got the horizontal component. I need the velocity, right? So I know that the force is equal, in this case, to the tension, but the force is also a centripetal force. So that centripetal force was the mass times v squared over r. Okay? The v is what I'm solving for. The mass is of the rock. The r is the length horizontally of that circle. So if that's in proportion to the tension component, right, that angle should be the same for the forces as it is for the lengths, then I could do, in my proportions here, 200 newtons is equivalent to 199.76 newtons, as 1 meter is equivalent to the horizontal length there. So I'll cross multiply. 200x equals 199.76 Newton meters. Divide by 200. Divide by 200 gives me a value 0.99879. It's effectively 1. So really, I barely have to consider the horizontal. 0.99 878. Doesn't matter how far I round it, I'm still rounding it to 1. 8798779. There, I don't know how to, yeah, not round it to 1. So the angle is so small there that I think it's kind of irrelevant. In the textbook, they really considered that angle. They calculated it as 2.81 degrees. And so I wonder if I'm doing something wrong there. 2.81. I'll double check it just to see, because, well, let's see. If I did it right, then cosine of theta is equal to the opposite, 9.8 over the hypotenuse. No, opposite over hypotenuse is sine. Opposite over, no, it's cosine. So sine, opposite hypotenuse, sine. Dang, guys, sorry. It is late on Friday as I am recording this. So the sine of theta is 9.8 over 200. So if I do 9.8 divided by 200, enter sine of the answer 2.8. Okay, good. So I'm doing it right. So theta is 2.8 degrees. I don't actually think that's relevant though, because by the time I take that length, it's effectively 1. So I'm just going to use the 1. Even though I took into account the verticality of it, it didn't matter because it's such a tiny angle that I think it's pretty darn irrelevant. So I'm going to end up rounding that to 1 meter and using that for my length. Thanks for taking me on that goose chase, textbook. Now, it might matter if there was less tension or if there was a heavier object, but for our purposes, I think you're okay. So the radius is going to be 1 meter. The tension is 200, so I'm going to go ahead and plug in there. 200 newtons equals the mass, 1 kilogram, times v squared, over the radius, which is 1 meter. Look at that. Those suckers are both 1, so that doesn't do much. Take the square root of both sides. Square root of 200 should be just over 14. And indeed, it is 14.1. So my exit velocity is 14.1 meters per second. Okay. That is my horizontal exit velocity. So now over here, I go back to my diagram, and now I need to figure out the time that it took to fall. The falling time, since it started at rest, I can use my equation for a falling object, which was the change of y is 1/2 at squared. I know that my vertical height was 25 meters, is 1/2 9.8, I guess negative 25 meters, negative 9.8 meters per second squared. T squared, half of 9.8 is 4.9. 4.9 meters per second squared. 25 divided by 5 should be pretty darn close to 5. Negative, negative. 25 divided by 4.9, 5.1, indeed. Second squared equals t squared. T equals 2.26 seconds. All right, I got 2.2 seconds. I have 14.1 meters per second. I was up here. So now I can say from this equation right there, x equals Vxt, plug in the two pieces that I figured out, x equals 14.1 meters per second times 2.26 seconds. X equals 31.9. Let's just go ahead and round her to around 32 meters. I believe that the rock landed 32 meters from the base of the cliff. That is a pretty darn good throw or fling, but it could have landed as far away as the 25. Seems reasonable, not an outrageous number. I am feeling pretty good about that answer, and it happens to track with the one that the textbook got as well, just in a different way. All right, my friends, way to stick with this one. So we are going to zoom back out. You are going to run some practice problems. Those practice problems are going to be all of the multiples of 5 for chapter 6. And we've only got the one chapter this week. Hooray! Enjoy, my friends. I think mostly this is just using some different equations. And I think you should know how to do it. Lots of equations to choose from. Enjoy.